Students, last time we already discussed some examples of addition reactions to the carbon-carbon double bond, and we already discussed the addition of HX, or we call the hydrohalogenation reaction, and in which product is a major product, or the product is according to the Markovnikov addition. So in case of Markovnikov addition, what happened? The negative part of the reagent, which is attached to the carbon which carries the less number of hydrogen atom, and this rule is called as a Markovnikov addition. So today we are going to discuss the next part, and that is a Antimarkovnikov addition. So what happened in Antimarkovnikov addition? The product is against the Markovnikov addition. So means what happened in case of Antimarkovnikov addition, or sometimes we call the peroxide effect. And in case of the Antimarkovnikov addition, the negative part of the reagents which is attached to the carbon which carries the more number of hydrogen. So means in Antimarkovnikov addition, the product is opposite to the Markovnikov addition, and sometimes we call the peroxide effect. This Antimarkovnikov addition sometimes we call it the peroxide effect. We take one simple example, and suppose we take this starting compound alkene that treats with HBr, and then there is a formation of products. I write here the major product, and this is a major product. So this addition is according to the Markovnikov addition, and we get this is a major product. But when you take a same starting compound, you take a HBr, and reaction takes place in presence of H2O2 peroxide. So the product is different, and when we write a major product, then we get this is a major product. And so this addition is according to the Antimarkovnikov addition. So this is a simple case. You take a same starting compound, reaction takes place in presence of only HBr, then which is a major product, the 2-bromo-propane as a major product, and this product is according to the Markovnikov addition. But when you take a same starting compound, we add HBr or addition of HBr in presence of H2O2, the product is different, and we get a 1-bromopropane as a major product, and this reaction is according to the Antimarkovnikov addition. So that's why due to the peroxide we get a different product, and that's why the peroxide effect, or sometimes Antimarkovnikov addition, is also called as a peroxide effect. So what is the role of H2O2 in the reaction? When there is no H2O2, the product is different. When in presence of H2O2, the product is different. So what is the role of H2O2? So we remember in this case, so we see the mechanism of this reaction. Means we see what happened in presence of H2O2, what is the mechanism of this addition reaction. And when we think about a mechanism, so the mechanism takes place by free radical waves. When the reaction is carried out in presence of H2O2, this reaction follows the free radical mechanism, and that's why according to the Antimarkovnikov addition, the major product we get in presence of H2O2. So what happened in case of this H2O2? We know there is a peroxide is there. This bond between two oxygen, it is weak, and this bond is break, and we get the hydroxy radical. So this is the first step. This reaction is carried out in presence of peroxide. The bond between these two oxygen is break, that is homolytically, and we get this is a hydroxy radical. When this hydroxy radical reacts with HBr, and what happened here? Again, this hydroxy radical is abstract or take the hydrogen from HBr, and then there is a formation of this Br radical and one water molecule. And so this step we call chain initiation. So this is the first step in this mechanism, the mechanism of addition of HBr in presence of H2O2. So this we know this mechanism takes place by or follow the free radical way. The peroxide, the bond between oxygen is break to form the hydroxy radical. This hydroxy radical is abstract the hydrogen from HBr, we get a Br radical. And actually in presence of H2O2, which part or which is added or which species is added to the carbon-carbon double bond? The Br radical is added to the carbon-carbon double bond first. So what happened in this case? In second step, what happened? Once you write a reaction, you take this is your starting compound. After chain initiation, we get a Br radical. And actually this Br radical reacts with the carbon-carbon double bond. And such cases, there is two types of product formation takes place. When this Br radical is added to the carbon-carbon double bond, then we get such type of radical or secondary radical. This is one intermediate, and we get this is a secondary radical, this is a primary radical. So we get these two intermediate, and once we get these two intermediate, then we get two products. So how to get two products? Because there is a HBr, here is again the HBr is there. So this radical is abstract the hydrogen from HBr, and we get two products. So I write the first product. This is the first product. I write a second product. But we remember here which product is a major. So the first product is a major. This is a major product. And this product is according to the Antimarkovnikov addition. This product is according to the Antimarkovnikov addition. So why this product is major product in presence of H2O2? So that's why we see these two intermediate. So what is the mechanism? Free radical. First the hydroxy radical is generated. This hydroxy radical reacts with a HBr. We get a Br radical, and actually this Br radical is added to the carbon-carbon double bond, and we get this type of radical. But we remember here, this is two compounds. Here the secondary radical is there, here the first primary radical is there. So we remember well, as like a carbocation, the tertiary carbocation is more stable than secondary and then primary. So similarly, the radical stability is like that. Secondary radical is more stable than the primary radical. And so that's why which is a major product? So this is a major product, and according to the secondary radical, which is a major product, we get a 1-bromopropane as a major product, and this product is according to the Antimarkovnikov addition. And we remember well, only HBr gives the peroxide effect, or the HBr gives the Antimarkovnikov rule in presence of H2O2. So we remember why the Antimarkovnikov addition or Antimarkovnikov product is a major in presence of H2O2, because reaction follow the free radical mechanism. We generate these two intermediate. Secondary radical is more stable than the primary radical, and that's why we get a 1-bromopropane as a major product, and this product is according to the Antimarkovnikov addition. Then we take a next example, and there is another example, addition of halogen. The addition of halogen means X2. The addition of Br2 or addition of Cl2. Then there is a formation of vicinal dihalide. Vicinal dihalide. We take one simple example. Suppose this is a carbon-carbon double bond. They reacts with the Br2 in presence of inert solvent CCl4. Then we get This is a fissional dihalide. So what happened in this case? This reaction is carried out in presence of the inert solvent. Then we know what happened, the decolorization. We know the decolorization of the Br2 water is a classical test for the unsaturation. You know, in laboratory, what is the test for Br2 water? Means when your compound is saturated or unsaturated, that's why we take a Br2 water test. And when we take your compound and add the Br2 water, the decolorization of Br2 water takes place, then it is a classical test for the unsaturation. Then in this method we synthesize the various fissional dihalides. Then what is the mechanism of this reaction? The next part, the mechanism. And when we want to write a mechanism, then we take one simple example and then we see what is the mechanism of this reaction. This is your carbon-carbon double bond. We add, suppose, the Br in presence of CCl4. This step is the first step. It is a slow step. What happened? Br having the delta positive, one having the delta negative. This electrophile is added first, then this Br is leave out, and then there is a formation of bromonium ion, we remember. So here this is a bromonium ion. The bromonium ion formation takes place, and once the bromonium ion formation takes place, we get here the Br. So this is the first step. So step first. What happened in step first in addition of halogen? When you are taking alkene, that reacts with Br2 in presence of, this is an inert solvent like carbon tetrachloride. The first step is a slow step. This electrophile is added to the carbon-carbon double bond first, and we form the cyclic bromonium ion. And once the cyclic bromonium ion formation takes place, then the step second is there, and in second step, the cyclic bromonium ion is open. And how this cyclic bromonium ion is open, we remember like that. Then you having your Br minus or nucleophile in your reaction mixture, it is attacked from the opposite side, and we get this. And this is second step, and we take, it is a fast step, and we know there is a anti-addition of Br takes place. And when the anti-addition of Br takes place, then we get the product. We write this anti-products or 1,2-dibromo or fissional dihalides. These type of compounds we get. So this is a simple example. This the addition of halogen takes place by the two steps. In first step, the electrophile or the Br with a positive, delta positive charge, it is electrophilic in nature. They added first to the double bond, and then there is formation of a bromonium ion. Once the bromonium ion formation takes place, you are having the Br minus in your reaction mixture. This Br minus is act as a nucleophile, and it is attacked from the opposite side of this Br. And that's why this addition is an anti-addition. Means addition of halogen takes place by the anti-addition, and both the Br, they are attached to the opposite side in the product. So that's why this Br is attacked from the opposite side of this Br, and then this cyclic bromonium ion is unstable, it is cleave, and there is formation of a fissional dihalide. So this is a simple mechanism. But what is the support for this mechanism? So there are the two or three points is there, and this support for this simple mechanism of addition of halogen. And so what is the first support? The kinetics. So what is the kinetics of this reaction? The kinetics of this reaction shows that rate of the reaction depends on the Br2 as well as the alkene. So that's why what is the first step? First step is a slow step, and in the slow step both the molecules, they are taking part in a reaction. So that's why what happened here, in addition of halogen, or what is the support of this reaction is a bimolecular reaction, because the rate of the reaction depends on the alkene as well as a reagent, that is a Br2. That is the first support. Then structure of alkene and the reactivity. This is second support is there. Means what is the structure of alkene is depends on the what is the reactivity of that particular alkene. Means when what happen when alkene having more and more electron donating groups, then what happen, the rate of the reaction is more, and when the alkene having electron withdrawing group, then the rate of reaction is slow. So that's why what happen when electron donating groups were attached to the alkene, then it activate the alkene and the rate of the reaction is increased. When you take electron withdrawing groups, they are attached to the carbon-carbon double bond or alkene, then what happen, it deactivate the alkene and then the rate of reaction is decrease. So this is another support, means what is the structure of alkene, it decides so what is the rate of reaction. Electron donating groups are attached, then it activate the alkene, the reactivity is increased, rate of reaction is more. But when we take electron withdrawing groups, they are attached to the carbon-carbon double bond, it deactivate the alkene or double bond, and then ultimately the rate of reaction is decreased. So this is the second support. And the next support or last one, the effect of added nuclei. The effect of added nucleophile. So what happened in this case? What is the effect of added nucleophile? Means, you know, we take simple example. Suppose this one here, Br2, formation of cyclic bromonium ion, this one, and again once you having the Br minus in your reaction mixture, this act as a nucleophile, but we added the various nucleophiles. Means here we take a simple nucleophile, we add a chlorine as a nucleophile, we add iodine as a nucleophile, then again you add a cyanide as a nucleophile, or in this way we take H2 as a nucleophile and we are in your reaction mixture. So what is the effect of added nucleophile? Means you take this simple alkene, then Br2, then formation of cyclic bromonium ion. And what is in your reaction mixture? There is Br minus. So Br minus is your nucleophile which is present in your reaction mixture. But we add externally this nucleophile. We add Cl minus, we add I minus, we add Cn, cyanide, H2, Br minus. Then what happen? Then this nucleophile is also open this cyclic bromonium ion, and there is a formation of this type of product. Then when the iodine is also attack on the cyclic bromonium ion, and there is a formation of such type of product. Then when there is a Cn or cyanide is there, the cyanide is also formed, so this type of product. So what is the effect of added nucleophile? Means we add a nucleophile, this nucleophile is also open the cyclic bromonium ion and to form the various product. Means what is the meaning of this? When we form this type of product or this type of product, and this nucleophile is attack on the cyclic bromonium ion, it proves that in addition of halogen, there is a cyclic bromonium ion formation takes place. And when the cyclic bromonium ion is formed, then we add a nucleophile, various nucleophile, then these various nucleophile open the cyclic bromonium ion ring system, and there is a formation of a different type of products. So this such type of product formation takes place, and we added this type of nucleophile, it indicate that, or it support the formation of cyclic bromonium ion in addition of halogen reaction or in addition of halogenation. Then the next example, or that is a hydroxylation reaction. So you see the next example, that is a hydroxylation. And in hydroxylation there is formation of 1,2-diols. So what happened in case of the 1,2-diols or hydroxylation? So hydroxylation is nothing but addition of hydroxy group to the carbon-carbon double bond, and we form the 1,2-diols. So what happen in case of this hydroxylation, we use that is a KMnO4 or OSO4, osmium tetroxide. These two reagents we use for the hydroxylation, and we use these, then we get a cis hydroxylation product. So we want to both the hydroxy group from the same side, or we want a cis hydroxylation product, then we use these two reagents, KMnO4 and osmium tetroxide. Suppose here we take one simple example, and then we see, so suppose this is we take a cis-2-butene, and the cis-2-butene, they are reacts with KMnO4, and this oxygen from the KMnO4 is labeled by oxygen 18, and then we get a intermediate and we get the cyclic, the manganate ester, and both the oxygen is coming to this, it is O18 labeled. And when this cyclic manganate ester is hydrolyzed, and after hydrolysis we get the 1,2-diol, this one, and in this case we get the meso product. Meso 1,2-diols. So what happens, we see the this is a simple example, and what is this is the example of cis hydroxylation. We remember well, we want to do the cis hydroxylation, we use a KMnO4 osmium tetroxide. So that's why we remember this is cis-2-butene, and when the cis-2-butene they reacts with the KMnO4, and in alkaline KMnO4, then what happens, there is a formation of cyclic manganate ester. And when there is cyclic manganate ester formation takes place, this is a cyclic manganate ester. And we remember that this oxygen from the KMnO4 is labeled by oxygen 18. And when they are labeled by oxygen 18, then we see the cyclic manganate ester. So both the oxygen is coming from the KMnO4. So no any oxygen from the product is coming from the water molecule, but both the oxygen they are coming from the KMnO4, and so that's why this is cyclic manganate ester formation takes place. Then the cyclic manganate ester is hydrolyzed in presence of water and NaOH, and then there is a formation of a meso 1,2-diol. So we remember, we start from the cis-2-butene, then we do the cis hydroxylation, then we get a meso product. So this is simple example, the addition of KMnO4 in presence in the carbon-carbon double bond, and there is formation of 1,2-diols.